Dr. Aliasgar Arab. I'm presenting the work safety prioritization by iterative feedback linearization control for collaborative robots with my co-author, Dr. Yashar, Dr. Kayan, and Dr. Ibrahim. This paper was done as part of independent research when I was affiliated with New York University in North Carolina, Agriculture and Technical State University, and also co-founded my company, General Autonomy. And Dr. Yashar and Dr. Ibrahim are affiliated with GCU, and Dr. Kayan is affiliated with Birmingham University. This research is about how to prioritize robot motion around human based on the most critical point of the body. So if the robot is moving around head or around body, the robot should understand that and should address that accordingly. We proposed a new method and we will be discussing it in this presentation. So why we need more advanced control systems? The reason is we are increasing the use of collaborative robots, and number of the robots working around human are increasing every day. You can see people's head and people's hand are very close to robot when they are working with them in the industrial environment, or even less industrial environments like a research lab or even like a medical lab or biomedical lab. So these understanding of the self and the other for robot is very important. I think the understanding of the self, where the body of the robot is, like each joint and each part of the arm. So that is feasible through understanding the joint angles, but understanding the human presence and accurate and precise human body is also very important to make robot work efficient and smooth around human when they are like in a collaborative work environment. So when robot is working around human, it's very important to understand where are the most critical part of the body, like head or even eye or other parts. So this paper is only prioritizing head over the rest of the body, and head is getting the highest priority. So when the robot is moving around head, it will keep more cautious constraints. And also the robot should move smoothly around human to give both physical and psychological safety when a robot has an aggressive motion around human body. So that psychological safety is affected. So this controller is using iterative feedback linearization and integrating it with nonlinear model predictive control, and defines safety prioritization to make smooth and safe motion around human body. The necessity for a novel approach is important because like existing methods are limited, so it's good to explore other methods. However, like some of them like control barrier functions and even like nonlinear model predictive control, they have proved that they are able to address safety, but addressing both safety and smoothness and how to prioritize them is still like an open question. And recent research are working around it. Feedback linearization is a very strong tool in terms of giving you capability to adjust the controller because it brings the output in a linear format, KP, KD, like the PID gains. We can adjust them to adjust the performance of the system. So it's good to bring the system in that format, but all the systems are not feedback linearizable, of course. But we only put that feedback linearization as a constraint in our model predictive control instead of trying to feedback linearize the controller. And we integrate the safety prioritization into our constraints of model predictive controller. So the reason we had to combine these two, it came from this table, simple table, like based on pros and cons of the NMPC and FLC. They are both reliable and stable controller. They have been used across the industry. and academia, of course. And we can see FLC simplifies the parameter tuning, and it allows you to get the performance that you expect with a few adjustments. However, NMPC has more difficult adjustment and tuning scenario because still each cost function might treat the system differently, and like the whole system is based on the cost function that you are defining. And feedback linearization cannot address constraints, so it's not a popular method for safety critical systems when we have to address constraints, but NMPC, because of using nonlinear programming in real time, is capable of addressing the constraints. And by combining these two methods, we can take advantage of simplifying the parameter tuning and also adding the constraints to the control system. So to formulate the problem very like a basic definition, we have a nonlinear system, x dot is equal to fx and u. X is the state of the system. Any states can be here, like the joints of the robot, the distance from robot to the human, and all these things can come to the state of the system. So it depends on how granular we want to get. And the output is robots and effector, and we want to control the system in a way that all the state of the system, robot's joint, and relative distance of robot to the human body are in the safe set. We call them XS. And the right figure here is showing that if we want to get from any initial point to the target point, which is the center of this eclipse, we might be able to go from a fully safe and stable region. We might be able to go from only stable region, but not safe area. So the area around the non-safe area, we call it cautious. So if the robot is entering that area, is going to exit that area before entering the unsafe region. So we can see we have to prioritize the robot motion to avoid cautious. So if the robot enters the cautious area, we will try to move out. And unsafe region is a completely avoided area. So even the robot is not going to get to the target, and we cannot find a safe trajectory. A very high level architecture of the controller, we have the safety requirements, like the robot not hitting the human head. Robot, if hits the human body, should be with like very controlled force and no injury. And the requirements are defined as constraints. We have the initial path of the robot through the planner. The planner gives the trajectory to the controller. The controller has the state of the system. And the nonlinear programming of nonlinear model predictive control system has both robots model, and it has some predictive models for human motion. Formulation of this problem, we have the objective function, which is feedback linearized output as a constraint. So we want to make sure the output of the robot is linearized, which it gives a smoothness to robot behavior. And we optimize the gains for that linearized output, which is kx. And we want to get the highest performance by that optimization, and also checking that the robot will not enter the unsafe region. And the safety set is the area that all the safety constraints are met. So we have to make sure we are getting to the set that all the safety constraints are there. And if any of them are not going to be satisfied, the lowest priority should be the one that is going to be dropped out from our safety list. And the top priority ones will not be sacrificed at any situation. And each safety constraint will be defined by a barrier function as a B. And by adding all these functions together and putting a weight on it, we can prioritize them. This table shows a safety indicator for this application. The safety indicator is summation of all the potential safety constraints by defining a barrier function for them and adding them together. And the predictive controller will make sure that safety indicator is not violating the safety values in the predictive horizon. And this table shows the priority. Priority 1 is the priority that shouldn't be sacrificed at all. Priority 2, there is a chance, but it should be controlled. And priority 3 and 4 might be sacrificed in certain scenarios. And this is a picture of showing the robot moving around human body, one of the Baxter collaborative robots in our private research lab in New Jersey. We only programmed the robot to move 2 joints to experiment this to simplify the problem for this scenario. The robot will only move the arm, and the target is to move it from the top of the head to the bottom of the head, and it will make sure that there is no contact around head, and if it's a contact around body, is a smooth contact. Robot starting from initial point, getting to the final point, comparing NMPC with the safe iterative feedback linearization. We can see the safe iterative feedback linearization is having smoother motion by only the line, but we will have a comparison table in the next slide. Only by comparing the linearity of the output, which is our definition for smoothness, and the safety indicator value, we can compare our safe iterative feedback linearization with safe NMPC and a simple control barrier function method without any prioritization in that. So we could see that our proposed method is getting higher safety indicator value comparing to the other methods and still getting smooth output. The convergence time for all of them are similar because they have to solve the nonlinear programming in real time. However, feedback linearization control is not capable of solving nonlinear programs, so that's why we have not applicable. Feedback linearization control might hit the human body at any scenario, if only and if the human body is not in that region. And we can see the NMPC has like higher velocity motion comparing to safe iterative feedback linearization. And the convergence time for both are very similar, even though the NMPC performance is getting to the faster motions. But it means that we have like more aggressive motion around humans. We introduced a feedback linearization technique combined with NMPC. Instead of like linearizing the system, the nonlinear system, we added the feedback linearization as a constraint in NMPC. And we defined safety indicators and linearized output indicator to measure the safety and smoothness of the robot. As a conclusion and future work, this method can be implemented on various type of systems, even non-holonomic systems or non-affine systems, since we are putting the linearized output as a constraint to nonlinear model predictive controller. So that will give us an advantage in instead of just linearizing the nonlinear control systems, because for a non-affine system, we cannot easily linearize a system. And in our future work, we want to test similar method on other type of robotic systems. And thank you so much.